In this video, we are going to write an augmented matrix. We're going to write the system of equations in an augmented matrix form. We're going to do row and not column operations, not in this video, on a matrix. And we're going to solve a system of equations using matrices. So we're going to start with a warm-up in which I'm asking you to solve the system. Now, if I asked you to solve the system, you have multiple ways. One is to graph it and see whether or not it actually processes at nice integer numbers on the graph. Another way is by substitution, and I wouldn't choose substitution for this one. And the reason I wouldn't do substitution for this system is because if I solve for x with the first equation, I'm going to end up with a fraction of 37 over 8. If I solved for y, then I'm going to end up with two fractions, 8 over 37, and this other 8 over 37. Similarly, if I took the second equation and did a substitution, so I'd have to solve for either x or y. Solving for either x or y in this second equation is going to produce a fraction when I divide either the 3 by the 2 or the 3 by the 12, those being the coefficients on x and y. So I'd be more likely to do elimination. And I can see that it's going to be easier to eliminate the x's simply because 2 and 8 have a multiple of 8. So I can just take this second equation and multiply by a -4 and then add the two equations together. So I'm going to take this and multiply by a -4. The first equation, 8x minus 37y is equal to 8, does not change. The second equation becomes -8x, and then this becomes a minus 48. Still not feeling 100%, so gotta bear with me. So a minus -48y, and then equals a -12. When I do this, these two equations, the x's will cancel themselves out, leaving me a -37 minus 47 more. And I'm going to get my calculator out because, again, I'm not feeling terribly well. And I assume that this is not going to go well if I try to do it in my head. So this gives me a -85y. And then on the other side of the equal sign, I have 8 minus 12, which is -4. So my y, divided on both sides by the -85, is -4 over -85, which is just 4 over 85. Double negatives make it positive. So once I found my y, I can put that back into one of the two equations, and either one of them, they're not terribly nice. And what I mean by that is, whether I put it in for the first equation or the second equation, the -37 multiplied by 4 over 85 is not going to cancel out the 85. Same thing with the 12. So it doesn't really matter. So I'll just might as well put it in the second equation. So I'm going to have 2x plus 12 multiplied by 4 over 85 is equal to 3. So I'm going to go ahead and move the 48 over 85 to the other side. 2x is equal to 3 minus 48 over 85. And then I'm going to go ahead and make a single fraction on the left-hand side. So I'm going to take that 3, I'm going to multiply by 85. And I get, let me erase this. Well, actually, let me write down what y is. So y, I'm going to write it over here. Y is equal to 4 over 85. Okay, so now I'm going to just erase this so I can have this space. So I'm going to get on the left-hand side just 2x still. And then on the right-hand side, I'm going to do 3 subtract 48 over 85, which gives me a 207 over 85. And then now I'm going to divide by 2. So I'm going to get 207 over 85 times 2. It's 170. So my answer is 207 over 170, comma, 4 over 85, which obviously are not integers numbers. So I couldn't have done this by graphing anyways. I could have done substitution, but I would have had to deal with fractions. I chose elimination, and I still ended up with fractions. So just like we have synthetic division to help us with division of polynomials, we also have a way to make our systems of linear equations a little bit easier. And the way in which we do this is we do something called an augmented matrix. And that's what this is. This is an augmented matrix. So I peel off the coefficients, just like in synthetic. I peel off the coefficients on the x, y, and z, and they're going to go, for the first equation, is going to go in the first row. This is a coefficient for x, y, and z. And then I put this line here. Now this line helps me to know that everything on the right side of that line were the constants. So that was where the 4 came from. The second row is the second equation with the coefficients peeled off, and then the constant. And the third equation is the third row with coefficients pulled off and the constant here. So the first column then represents all of the coefficients on the x's. The second column represents all the coefficients on the y's. The third column represents all the coefficients on the z's. And then the last column represents the constants. This is an augmented matrix. Now, if I pull off the constants 4, 3, and 0, I get a coefficient matrix. So I have 3 equations and 3 unknowns, so I expect my coefficient matrix to be 3 rows and 3 columns. So again, from our last video, we talked about the matrix. We do the number of rows first, and then the number of columns. It's the augmented matrix was a 3 by 4. The square matrix was the coefficient matrix. The things that I'm allowed to do is I'm allowed to interchange rows once it's in matrix form. And the reason I'm allowed to interchange rows in matrix form is because I can interchange the way in which I work with the equations. When they're linear equations, I can write one equations 1, 2, and 3 as equations 1, 3, and 1, or 1, 3, and 2, excuse me. So I'm allowed to do that. I'm also allowed to multiply a single row by a non-zero constant. And notice how we denote the notation here. And I'll go through a process of doing one of these and what the notation I would expect to see. And the reason we do the notation is so that if you do make a mistake, you can go back and look at your notation and see what you did, and then actually check to see if you actually did that appropriately. So that's why we do the notation. And then we just multiply a single row. And the reason we're allowed to do that is if we look at our example from our first starting point, notice how I multiplied this equation by the -4. So I can actually turn this matrix, I can turn this into its matrix. So the first row is the coefficients 8, -27, and line, and then 8. The second row was 2, 12, and 3. And that is my matrix. What I did was I took -4 multiplied by row 2 and put the answer back into row 2. So matrix form was 8, -37, that should be 37, not 27, and 8. And then when I multiplied by that -4, this became a -8, this was the -48, and this was the -12. Okay, so that's what we mean by being able to multiply by a constant. I can also add two rows together. So here I'm going to add two rows together. And how would I do that on my example? Well, in this case, what I did was I added row 1 and row 2. So I'm going to take row 1 plus row 2, and we typically put it in the second row or third row or whatever. We usually leave row 1 alone. So I'm going to put the answer back in row 2. And when I did that, I had 8, negative 37, and 8. This became 0. And then, what did I get that to be? 85? I think that was 85. Yes, negative 85. And then I had negative 4. And so this is where I was when I found that addition of those two equations. Then what this allows me to do is I can take this last row, and what I have is I have 0 times the x, which is what we got when we added the two equations, minus 85y is equal to the negative 4. Now, we don't typically write 0 times x, so I'm not going to. And this last row allows me to solve for y, which was 4 out of 85. Because, remember, this is my x's, this is my y's, and these are my constants. This last row tells me I have negative 85y is equal to negative 4, and that allows me to solve for y. And by using it in matrix form, it kind of cleans up the process. Okay. So, when we are doing matrix operations and we're taking a system of equations and turning it into a matrix, our goal is to try to get to a Gaussian elimination. Now, a true Gaussian elimination will have ones in the diagonal and zeros below the diagonal and whatever numbers are up here. And the reason we do that is because we can take this last row right here. Remember, this is the x, this is the y, and this is the z. This last row tells me 1 times z is equal to negative 1/2. And when we put it into Gaussian form, I can immediately find my z. And I also know that it tells me whether or not I actually have any solutions. Now this is row echelon form. It's Gaussian elimination sometimes is called row echelon form. Reduced row echelon form, RREF, is the best if you have a calculator to do it, because if you have a calculator to do the RREF form, you immediately know what all your solutions are. This tells me that z is equal to negative 1/2, and this one tells me y is equal to 7, and this one tells me that x is equal to 3. Because this is x times 1 is equal to 3, this is y, and this is y, times 1 is equal to 7, and since this is the z, this is z times 1 is equal to negative 1/2. So if your calculator does the row reduced echelon form, that's what you want, because it'll make it easier and you can go right to the answers. So if you were given an augmented matrix, your goal, of course, is to always, if you can, put it into row echelon form. In an ideal world, you'll have a 1 in this position, but it's not the end of the world if you don't. You can have whatever number in this position, but ideally you're going to have a 1 in this position. Now, I'm not going to test you on putting it into true row echelon form or even reduced row echelon form. And the reason is because all we're doing at this point is trying to solve systems, and we're not really getting deep into matrices in and of itself. Now, when you do your row echelon form, or you get it into somewhat row echelon form, I say somewhat because I'm not going to check to make sure you've got ones in this diagonal. There are times in which we are going to get something that looks like this. When this happens, we have an entire row of zeros, then that tells us that we have an infinite number of solutions. So if you haven't already done so, watch the video for 9.1 and 9.3. When this happens, you have to parameterize. You actually have to write your answer in terms of z or t. And so you'll have, as this example, let's go ahead and do this example as a solution, just as a reminder, what we did in the 9.1 and 9.3 video. As I said, z is equal to z, but now I'm going to use t, and it doesn't matter if I put this on the test. It doesn't matter if you use z or t. On the homework, it's going to tell you which variable to use. So then this is y minus 4t is equal to 20. So y is equal to 4t plus 20. And then this one tells me that x plus 9t is equal to negative 3. So x is equal to negative 9t minus 3. So my solution is going to be negative 9t minus 3, because that's my x. My y was 4t plus 20, and then my z was just t, and there's my solution. We have parameterized our solution. Okay, so now we're going to solve the systems using matrices, and I'm going to zoom in so I have lots of space to do the writing. So when I solve using matrices, since this first equation does not have an x, I have to put a 0 as a placeholder in the x position. And then I have 16, and then I have 4, 9, negative 1, and 2. Put the line there to tell me that on one side I have the coefficients, and the other side of that line I have the constants. Now, I'm not going to do a row echelon form, and the reason I'm not going to do a true row echelon form is because that this tells me already 16y is equal to 4, that means y is equal to 1/4. And since y is equal to 1/4, I can put it right in here, and I didn't actually have to solve this by matrices, but I did want to show you what happens when you're missing a variable and how to deal with that. All right, so now I have 9x minus 1/4 is equal to 2. So 9x is equal to 2 plus 1/4. 9x is equal to 2 plus 1/4 is 9/4. Divide both sides by 9, and I get 1/4. So my answer as an ordered pair is 1/4 for the x and also 1/4 for the y. These are ordered pairs. Let's take a look at the next example. I'm going to go ahead and write my matrix. So 3, 2, 10, 3, negative 6, 2, 5, 13, 0, because this one here, oh, it's not the x that's missing, actually. Gotta pay attention. I have an x, I have a 4. What's missing is the y, 1 for the z, and 18. Okay. So what I'm going to do is I'm going to take, and my goal is to, if you read the directions up above on putting this into row echelon form, true row echelon form, I would first divide everything by 3 in the first row. I'm not doing that because I'm going to end up with fractions, and I'm not doing it. So what I'm going to do then is I'm just going to leave it as is. I'm not going to change rows around. I'm just going to take and multiply whatever I need to multiply the first row and the second row by to eliminate and put a 0 here, and the same thing here. So I can do 2 row operations at the same time. So I'm going to take negative, or actually I'm just going to make 2 row 1 plus row 2, and I'm going to put it back into row 2. So my first row, 3, 2, 10, and 3, does not change. If I take the first row and multiply by a 2, this becomes 6, this becomes 4, this is 20, and this is 6. So what I like to do is I like to just put those numbers right up above, and I erase them if I need to, just so that when I do these numbers up above, so when I do the additions, I can really see the additions there. So I'm going to end up with 0, because 6 minus 6 is 0. And then I'm going to end up with 6, 25, and 19. At the same time, I'm going to do negative 4 row 1 plus 3 row 3 and put that answer back into row 3. So now I'm going to go back and I'm going to erase these numbers, the 6, the 4, and the 20. Now I'm going to multiply, excuse me, I'm sorry. I'm going to multiply row 1 by a negative 4, so this gives me a negative 12, a negative 8, a negative 40, and a negative 12. I'm going to multiply the third row by 3, positive 12, 0, 3, of course, 18 times 3 is 54. Okay. Now I'm going to add these numbers. The negative 12 and the 12, the 8 and negative 8 and 0, the negative 40 and 3, the negative 12 and 54. Get a 0 there and a negative 8 there. And 37, negative 37. And then 42. Okay, now my next goal is to put a 0 right here. Once I have a 0 right here, then I'm going to have a 0, 0, and then I'm going to have a number here is equal to a number here, which means I can find my z. So I'm done for right now with row 1. So the lowest multiple 6 and 8 have is 12. So if I multiply 4 times row 2 plus 3 times row 3 and put the answer back into row 3, then I'm going to have a 0 in that position. And again, if you're wondering what I'm doing, read through the directions on how to put this into row echelon form. It's earlier in the video, it's in the notes, it's in the book. Now, since I'm not messing with row 1 anymore, I'm just going to put that row 1, and I'm actually not really even messing with row 2. I am multiplying by a number, but since I'm putting the answer back into row 3, row 2 just gets repeated. So now let's go ahead and do this multiplication. This is 24, this is 100. Multiplying all of those entries by 4. This is 76. And then this gets multiplied by 3, so this is negative 24. Negative 37 multiplied by 3 is negative 111. And then 42 multiplied by 3 is 126. So when I add these two rows, this will become 0, and this will become negative 11, and then whatever that is. So I get 0, 0, and that's what I wanted, is I wanted a 0 in that position. So I'm going to take 100 and 100 and subtract off 111, which gives me a negative 11. And then I have 76 plus 126 is 202. And this tells me that my z, negative 11z, is equal to 202. Hopefully this will divide nicely, and it does not. So I get 202 over negative 11 is my z value. Now what we do is we are going to put that into the previous row. We're going to put it right here. 6y plus 25, 202 over negative 11 is equal to 19. 6y, actually I'm just going to give you the answer. Y is equal to, I get a 5,259 over 66. Now on the last one, that's this one, I have 3x plus 2 multiplied by that lovely 5,259 over 66 plus 10 multiplied by that 202 over negative 11 is equal to 3. And then whatever that equals is the x part. And then don't forget to write it as x, y, and z as the ordered triplets. Okay, let's take a look at this next one. I'm going to go ahead and set it up and go through it, and then I want you all to do the next one. So the first line is 1, 5, 8, and 19, and then 12, 3. There is no z, so I put in a 0, and 4, 3, 4, 9, and -7. Now this one is a much nicer one, just simply because it starts out with a 1 in this position. So I'm going to do -12 row 1 plus row 2 back into row 2. So -12, -60, -96, and then I don't know what 12 times 19 is. 12 times 19 is -228. Since the answer is going back into row 2, I have 1, 5, 8, and 19. Row 1 gets wrote down exactly as you see it. Row 2 becomes a 0, -57, -96, and then -224. At the same time, I'm going to take -3 row 1 plus row 3 and put the answer back into row 3. So again, I'm going to go ahead and erase these numbers. And I get -3, -15, -24, and then 19 times -3 is a -57. Okay, so this is going to give me 0, -11, -15, and -57, and this is -64. All right. Now I'm going to do, I usually like to work with much smaller numbers, but it doesn't look like, well, I think 57 is divisible by 3. Yep, and 96 is divisible by 3. And 224, I think, is divisible by 3. Nope, it is not. That is unfortunate. Okay. So now what I'm going to do is I'm going to take -11 row 2 plus 57 row 3, put the answer back into row 3. And the reason I have to do one negative and one positive is because they both have the same sign right now. So again, I'm going to rewrite this as 1, 5, 8, and 19, 0, -57, -96, and -224. And then this row is, the goal is to get a 0 there, so I might as well put a 0 there. So I'm going to do 11 times 57, and it's going to give me a positive 627, because it's a -11 times the -57. I'm going to do -96 times the -11, and I get 1056, and then 224 multiplied by the 11 gives me 2464. And then the 11 times the 57, which of course we knew was going to be the -627, which is why we get the 0 there. And then the 57 times the 15 is it's a -15, 855. And then the -64 times the 57, which gives me a -3648. So now I'm going to do the 1056 minus the 855. And I get 201, 200, 201. And then the last row, I'm going to have the 2464 minus the 3648. This gives me a negative 1184. I'm going to divide that by 201. So I get 201z is equal to a negative 1184. So z is a negative 1184 divided by 201. I'm going to write that as negative 5.891. I'm going to back substitute it here. So negative 57y. 57y minus 96 multiplied by the negative 5.891 is equal to the negative 224. I get my y to be 13.851. I'm going to put it into my top row. So x plus 5 times that 13.851 plus 8 multiplied by the negative 5.891 is equal to 19. So I get my x to be a negative 3.129. So my answer is, as an ordered triplet, negative 3.129, 13.851, and negative 5.891. Okay, so this, I believe, is the last one. I'm going to set it up for you. So pause it now. And I want you to see if your setup matches my setup. And then I want you to do the row operations. So go ahead and pause it. Do your row operations and see whether or not your row operations match mine. Welcome back. Hopefully this is what you got. And in this case, this tells me that 0 is equal to 2. 0 times z, if you really want, is equal to 2, and that's a false statement. So because we ended up with a false statement on this row, this bottom row is a false statement, there is no solution. And that's really nice with matrices because they shake out fairly quickly if you have a no solution. In fact, look, I basically did 2 operations but in one step, which made it really easy to determine this was a no solution. And that's it for this video.